Welcome to today's Explainer. We're jumping straight into some incredibly practical research today, specifically a paper titled A Low-Code Containerized Edge Architecture for IIoT Telemetry Orchestration, Mitigating Cloud API Rate Limits Through Dual Path Routing. This was authored by Jesus Rosa Bilbao from the University of Cadiz and published in the Sensors Journal with the DOI 10.3390/S2603082. So if you're interested in the actual nuts and bolts of industrial automation, smart factories, and the massive data challenges they're facing right now, let's dive right in.
98%. Just let that number sink in for a second. That staggering figure represents the catastrophic amount of telemetry data that simply gets lost when industrial sensors try to stream their raw information directly to rate-limited cloud APIs under heavy load. I mean, imagine running a state-of-the-art smart factory. You're generating thousands of crucial data points every single minute, and literally 98% of it just evaporates because the cloud service says, "Whoa, stop, you're sending way too much data." Honestly, that is the core problem this paper sets out to solve. Setting the stage, let's move into our first section, the industrial data flood.
To really understand why this massive data loss is happening, we have to look at modern manufacturing. Today's cyber-physical systems are everywhere on the factory floor, and they're generating huge volumes of heterogeneous data. Now, the old strategy was just to send all this raw telemetry straight up to centralized cloud platforms. But those pipelines, they're choking. They're buckling under severe bandwidth saturation, escalating compute costs, and really unpredictable network latency. The industry desperately needs a paradigm shift to solve this data flood. And that shift is edge computing. It's a distributed paradigm that relocates data processing much closer to its source. So instead of sending every single micro-vibration reading to a distant cloud server across the country, you process that information right there on the factory floor, maybe on a local gateway or an industrial PC. This absolutely slashes transmission costs, improves responsiveness, and it keeps your sensitive operational data safely in-house. But, as you might guess, actually implementing this isn't quite so simple.
Which brings us to our next section, the IT and OT convergence gap. So, the major hurdle to implementing edge computing is this gap between IT and OT. On one hand, we have operational technology, or OT engineers. These folks are absolute experts in equipment behavior, factory safety, and process control. But setting up edge middleware usually demands some serious proficiency in hardcore programming languages. Think C++, Python, or Go. And frankly, most operational engineers aren't software developers, nor should they have to be. This is where low-code development platforms step in to beautifully bridge that gap. By using open-source workflow automation tools like n8n, an operational engineer can literally route data, set conditional triggers, and manage telemetry visually, just using a drag-and-drop interface. Actually, instead of writing hundreds of lines of code, they're building complex data pipelines intuitively. Now, while low-code tools are pretty common for basic business processes, using them in high-throughput, latency-sensitive industrial environments, that's been largely unexplored, until now.
Let's look at the proposed solution in Section 3, the dual-path strategy. To test this visual approach, the author designed what they call a dual-path strategy. You can think of it as a highly intelligent traffic cop for all this industrial data. It's built entirely using containerized, low-code microservices to mitigate those public cloud rate limits, but without throwing away your precious edge data. It uses a three-layer edge architecture. Layer 1 is the physical data source. Your sensors and machines generating data using protocols like MQTT. Then, Layer 2 is the edge layer, which is hosted locally. Here, the data hits a local MQTT broker, flows into our low-code orchestrator, and is instantly saved to a local time series database. Finally, Layer 3 is the cloud layer, but here's the kicker. It's reserved only for high-level reporting and alerts. The data flows from the sensors directly into the local edge layer, completely sidestepping that direct, chaotic jump to the distant cloud.
This branching is what creates our two paths. First up, we have the hot path. This path guarantees 100% local retention. It's incredibly high speed and has minimal latency because it totally bypasses the internet. It's basically like having a local, high-speed security camera DVR that's recording absolutely everything that happens in the factory. Then, on the other side, we have the cold path. This path selectively forwards only specific critical events to the cloud. For example, it might only trigger if it detects a filtered anomaly, like a machine's temperature suddenly spiking above 80 degrees Celsius. Going back to our analogy, the cold path is like an emergency text message that only gets sent to your phone when the security camera actually spots a burglar. Let's see how this actually performs in Section 4, Edge Stress Test.
To see if this architecture could truly handle the chaos of an industrial environment, the authors subjected a single, low-cost Raspberry Pi 4 to a simulated ingestion rate of 3,000 messages per minute, and the results? They are dramatic. In a traditional cloud-only pipeline, the external API throttled the workload almost immediately, resulting in that catastrophic 98% rejection rate we talked about at the beginning. But when utilizing this dual-path edge architecture, outbound internet traffic was reduced by 98%. The cloud accepted the critical alerts perfectly, no throttling at all, while the edge retained 100% of the raw data locally with an incredibly fast processing latency of around just 5 milliseconds.
And what's truly remarkable here is how the hardware handled it. This robust, enterprise-grade data sorting was executed flawlessly by a constrained, ARM-based Raspberry Pi 4, literally without breaking a sweat. Throughout this intense high-throughput stress test, there was absolutely no thermal throttling. The CPU load was distributed super efficiently across the Docker containers running the MQTT broker, the orchestrator, and the database. And despite the orchestrator being a Node.js application, the memory footprint remained completely stable. It just goes to show that low-cost single-board computers have some serious headroom to run containerized, low-code middleware. Bringing it all together, we arrive at our final section, metadata and final reflection.
Ultimately, this architecture effectively neutralizes the manufacturing Tower of Babel problem. It completely avoids those dreaded HTTP 429 too many requests cloud errors, and it does it all without requiring a team of specialized software developers. It elegantly decouples high-frequency local data retention from low-frequency cloud reporting. Today, we've been exploring the paper, A Low-Code Containerized Edge Architecture for IIoT Telemetry Orchestration, Mitigating Cloud API Rate Limits Through Dual-Path Routing, authored by Jesus Rosa Bilbao from the University of Cadiz, and published in the Sensors Journal, DOI 10.3390/S22603.082. I want to leave you with one final question to ponder. If a simple, low-cost Raspberry Pi can orchestrate all of this flawlessly using drag-and-drop tools today, how will low-code edge computing reshape the massive, data-hungry factories of tomorrow? Thank you so much for joining me for this explainer. Keep learning, and I'll catch you next time.